Hey everyone, so today I'm going to talk a little bit more about the center of mass. Let's talk about the motion of the center of mass of a system of particles. For example, if I take, um, let's see, for example, if I have a particle moving like this, it has a definite velocity, say v, and you can get its displacement x, right? But if I have a system of particles, say I have maybe a rod or something. It's moving this way with the velocity v. So again, I will concentrate this full rod rather. I'll concentrate this rod at its center of mass and I will make it move. So I will say the center of mass is moving with the speed v. Alright. Now, um, let's talk about how the center of mass is not affected due to internal changes in energy. Alright. So all center of mass is independent of the internal changes of energy. You're probably confused. Let me just show you what I mean. Let's say I have a firecracker. Okay, it goes up like that, boom. It explodes into like bunch of pieces. Alright. If you take all of these pieces, they'll have individual velocities, won't they? They'll all have individual velocities. But they'll all have that one center of mass. If I say this was my rocket over here, over here, over here, the center of mass is going to be moving. And also, it's gonna stay unaffected. All right. How do I put it? It's all these particles moving over here. It's gonna be as good as this particle continuing in its trajectory, original trajectory. Let me give you a better example. Let's say I have let's say I have something, a projectile launched like this over here, and maybe somewhere over here it splits into say two parts. One part goes that way and the other part goes that way. Say maybe like that or something. This particle over here, I'm going to mark this in green. This particle in here is going to have it's going to have another mass m1, and it'll be saying moving with the speed say v1. Okay, let's say my original particle, it had a mass m and was moving with a velocity v. All right, so this is going with m1 and velocity v1. This particle has a mass m2 and it's going with a velocity v2. All right, so this is where it splits. Now, whether it splits or not, it's not going to be the center of these two particles are going to move and they will hit somewhere, and it's going to be as good as the center of mass, which will have continued its motion. All right. So basically, what I'm trying to say is the momentum is going to be the same. Oh, so if I say this, if I want to express it for this system, I can say that capital MV is equal to M1V1 plus M2V2. So this is by the law of conservation of momentum. If I say the LHS, if I see the LHS is the momentum for the center of mass. All right, and the RHS is the momentum for these two particles that have come out of this original particle. They've split up. So by conservation of momentum, this is going to be equal to this. So that's what it means. That's what I mean when I say the center of mass is going to be affected. Changes in internal energy. So this thing exploded over here probably because there was some internal energy, wasn't there? So it stays unaffected. So this thing is going to be really handy for all of you guys. When I say by law of conservation of momentum, let's take a problem based on this. For example, if I say I had a particle moving like this with velocity v, this particle had a mass m. Let me give it some quantities. All right. Wait, where to go here? let's say this particle had a mass 3 kgs, was moving with the speed say 5 meters per second, and at maybe some point over here it decides to split up, boom boom, like there's an explosion inside it. So it was a rocket, it explodes into two parts, and this is going in a straight line, this is going in another straight line. Let me say that these two parts, this particle has a mass m. Oh wait, I'm using quantities, hold on. Say this mass, say it breaks and it has 2 kgs and it's moving with a velocity of say 2 meters per second, and this one will have a mass 1 kg, but you don't know the velocity, so you have to find the velocity. What is the velocity? So I'm going to use that handy formula which we derived in the previous page. I can say mv is going to be m1v1 plus m2v2, isn't it? Substitute the values. 5 into 3 is equal to 2 into 2 plus 1 into v. So I get, if I solve this, I get v is equal to what's 25 minus 4? 21 meters per second. So that's how you solve it. That's how you get formulas like this and solve problems related to this. So so to summarize, if I have a particle moving with some velocity, then it's as good as its center of mass moving. And if it splits up into any number of pieces due to changes in internal energy, then the motion of the center of mass is not going to be affected, and momentum is going to be conserved always. Okay. Let's look at another problem. Okay, you've probably seen this in maybe movies like Gravity and Interstellar or something. So, say like there's a guy stuck in space, he's stranded, he wants to reach his spaceship. What does he do? He throws his helmet in the other direction, doesn't he? So that's conservation of momentum again, and it's related to the center of mass. So say I have a let's say this guy is over here, and he's holding his helmet in his hand, and he's stationary. All right, his spaceship is like here. He's lost, and his cord is broken, and he wants to reach here. How does he do it? He'll throw this over here with the velocity v, because I have to put signs and everything. He throws this over here, and since momentum is always conserved, when he throws this, he gets pushed back, because that's conservation of momentum, and also Newton's third law of motion. Every action has an equal and opposite reaction, right? So how do we put this in formula terms, right? How do we do that? How do we do that? Let's say this helmet had a mass m, and this big man has a mass capital M. Alright, and he's gonna move here with a velocity v1, which you don't know. So if you take normal conservation of momentum, or you can say the center of mass is originally stationary, isn't it? The center of mass was stationary. He didn't go anywhere. Only after he threw it, he's gone. And that's a change in internal energy again, isn't it? He's applying a force from within. So I can say that original center of mass motion, that my LHS of the equation, that's going to be 0, right? Because there's no velocity. So mass into velocity is going to be 0. And I can say over here, that's going to be equal to mv plus capital mv1. But these are vectors. Okay, I'm sorry if I'm going a little quick, but these are vectors, aren't they? The velocities are vectors. And let's say in my coordinate plane, I take this as positive and this as negative, right? So I'll say v1 is positive, but v is negative. So I'm going to put a minus sign over here. It's going to be that. So if I simplify this, I get mv1 is equal to mv, right? So I can say v1 is equal to mv by m. It's not like a hard and fast formula for you to learn or something. I just came up with something, a small example to show you how people use this center of mass concept. So for example, I'll say, let's go one level higher, all right? Okay, so have a look at this problem, for example. There's a trolley which is moving with a velocity v and has a mass m. And there's a boy standing at the origin of this trolley, like on the origin on this trolley, with a mass m1. Now what he decides to do, he decides to start moving to the right with velocity v1. Alright, so we have to find what, now when he does this, the velocity of this trolley is going to change. How and why, I'll tell you soon. Okay, I'll tell you now. So why does this happen? Because of conservation of momentum. All right, I can prove it to you through mathematics, like through formulas, which we will be doing in a bit. So let's first start by finding with what velocity does this system initially move. So when the boy was at rest. Okay, so for this you find the center of mass, but you find it with relation to velocity, not length. So basically you're finding with what velocity the center of mass moves. Now I haven't told you how to do this before, but well, I'm telling you now, so have a look. So the general formula was m1 v1 plus m2 v2 by m1 plus m2, wasn't it? But now what we're gonna do, you just I wrote v m1 l1 x1. Okay, so our general formula was m1 x1 plus m2 x2 by m1 plus m2, wasn't it? That was our original formula to find the center of mass. But when you want to find the velocity of the center of mass, so this is the position of the center of mass, right? Because using x, if you want to find the velocity of the center of mass, you replace this x with v. So m1 v1 plus m2 v2, it's that simple. If you want to find the acceleration of the center of mass, you replace this v with a. It's really simple. Now we're not dealing with acceleration over here because it's moving with a constant velocity. Alright. So that's the velocity of our center of mass. Now the mass of our boy is m1. We have that in account. His velocity is 0. So I can take this as 0. So this whole thing will become 0. You can neglect this. This is moving m2 v2. Alright, so that's gonna turn to mv, isn't it? It's going to turn to capital M into capital V by m1 plus m. That doesn't matter. So that's going to be our velocity of the center of mass. Now that's not going to change no matter what we do. All right, it's not going to change. That's what the conservation of momentum states. The law of conservation of momentum. This is the velocity of the center of mass, and no matter whatever happens, as long as that happening is inside, this is not going to change. So now I said my boy, he starts moving with a velocity v1. So when he starts moving with a velocity v1, this cart, its velocity is going to be less. So let's say my new velocity is v2. Okay, my new velocity is v2. And they've asked us to find the change in velocity, so we'll get to that later. My new velocity is v2, and v2 is going to be less than v. v2 is going to be less than v. Do you know why? Because if this boy starts moving in this direction, to counter that, this is going to have to reduce its velocity, because it's going to have to go in the opposite direction, which reduces v's value to v2. Like it's the same case as our astronaut and helmet situation, right? The astronaut, they're both at rest. Now the astronaut throws his helmet to one side, so to compensate for that, he goes in the other direction. So that's what's happening over here. And my velocity is not going to be the same, so I can keep this as 1. And if I find the new velocity, quote unquote, it's going to be m1 v1 plus mv2 by m1 plus m2, and we know that these two are equal, right? We know, so this is 1, this is 1, sorry, I don't have many colors. This is 2. I'm going to say 1 is equal to 2, right? So when I equate this, mv by m1 plus m2 is equal to m1v1 plus m2v2 by m1 plus m2. Wait, that was a capital M, wasn't it? I hope you're able to understand what I'm saying. I'm really sorry if you can't. Right, so these two can be cancelled right here. And simple, I get, okay, wait, now to the other way, right? So I get m1 v1, m2 v2 rather, is equal to capital M capital V minus m1 v1, right? And then I can say v2 is like the hidden, is like the unknown quantity, right? We already know v1, we already know v, so we have to find v2. So v2 is going to be capital M capital V minus m1 v1 by m2. Okay, that's again not a hard and fast formula. You if you know the concept, you can solve it. Just always remember, momentum is always conserved. If something goes in one direction, something is gonna have to go in the other direction to compensate for it. Now, for those of you who didn't get it, I'll solve and I'll give you, I'll use numbers, okay, and maybe that's gonna help. That probably help you. I'm gonna use like really different distinguishable numbers. Okay, let's say the same trolley situation again. Okay, there's a boy at the origin. Let's say the mass of the trolley is 5 kgs. Alright, and it's moving with a velocity, say 50 meters per second. Yeah, let's take 50 meters per second. And the mass of this boy is, say, 25 kgs. Alright, now let's find the velocity of the center of mass. What is that going to be? It's going to be 25 into 0. Okay, wait, I'll write on the base formula first. m1v1 plus m2v2 by m1 plus m2, right? Now we know v1 is 0, the boy is at rest initially. So I'm going to get 25 into 0 plus m2 is 5 into 50 by 25 plus 5, right? So that gives me, when you calculate it, that's 5 meters per second, right? Yeah, 5 meters per second. That's our velocity of the center of mass, and that, let's keep that aside. All right. Okay, so let me say this boy, he starts moving with the velocity 5 meters per second. Okay, so the velocity of the cart is obviously going to reduce. It's going to become v2. It's not going to stay 50 anymore, and v2 is going to be less than 50, as we discussed before. Now if I want to find the velocity of the center of mass, it's going to be 25 into 5 plus 5 v2 by 25 plus 5, isn't it? Like m1 v1 plus m2 v2 by m1 plus m2, right? Now let's equate it. You get 1 and this is 2, isn't it? So they're going to be equal, right? Because law of conservation of momentum. I say that too many times, but yeah, that's what you get. So LHS, that's here, and RHS, what we just got, that gives us, what's 50 into 5? 250 gives us 25 into 5 is 125 plus 5v2. That means 125 is equal to 5v2. So v2 is equal to 25 meters per second. And that's the new velocity of the cart, right? It's reduced by like half, so that's a lot. So that because this boy's mass is so much greater than the car, he moves by only 5 meters per second, and the velocity of the cart is reduced by half. All right. And yeah, remember, if they ask that what is the reduction in velocity, not what is the final velocity, so it's going to be this 50 minus v2. Like they probably ask by how much does the cart's velocity get reduced by, or something like that. So remember not to leave your answer just with this. You're gonna have to find this, and that's again 25 meters per second, isn't it? So this is a simple way to use like conservation of momentum along with center of mass. Thank you.